Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and if you step into my virtual classroom, it'll be an honor and a privilege to serve you today. I'm going to be looking at a few word problems that have systems of linear equations, and what we're going to do is create equations for them in order to solve, but I will not be solving them. That will be saved for a later chapter with my personal class, and that means for a later video. So today I have 5 practice problems for us to do. Within those practice problems, you'll be given a word problem situation. Let's go and take a look at the idea. You'll be given a word problem in a situation right here, and some general information about them. We're going to break it down by figuring out what we want to look for, and then we'll create variables as a result of that. And then afterward, we'll create 2 equations within the situations that have to do with the things that we don't know, but it'll help us provide context for what it is that when we do find it, what it means, and what those actual terms and coefficients and results and constants in the equations also mean. That's my goal for my personal class. This is something that can help you if you get problems like these ones as well. Okay. So for each problem, here's what I'm going to be doing, and here's what I would ask my class to be doing as well. Create and define variables, and I'll do it in a very specific way. You'll see what I mean. And set up 2 equations per problem because there's enough information for all that. So I'm just going to go ahead and dive into it right now. I'm going to start with number 1. And this one, it's actually kind of easier to make the equation for this one first because there's no real life context. But I'll give you an example of what setting up even variables for this one means, defining the variables. So let's go ahead and jump into it. Number 1, the sum of 2 numbers is 22. And their difference is 6. Now what I'm doing right now, putting these in different colors and underlining, not a necessary step, but what I'm doing is showing that there is enough information to create an equation for one situation and to create information for another situation. Both of them tying in the fact that I have these 2 numbers that I don't know. And look, you can guess and check, you can figure out, I think I already know what the numbers are. You could solve for it on your own, I guess, but we're not trying to do that here. We're just trying to set up the equations, and let's go from there. So there are 2 unknowns here. I'm going to go ahead and call them x and y because I know that they could be different, but they are going to be the same x and y for both equations. The sum of 2 numbers is 22, and their difference is 6. That means we're using the same 2 numbers we were talking about. All right, 2 equations. What are these 2 whole equations about? So the first one, the sum of 2 numbers, we're looking, sum is a result of adding 2 numbers together. So if I take the sum equation, it'll be made by adding my unknown x value with my unknown y value, and my result is 22. That's really what that equation is breaking down and saying right there. The second equation with the difference, and I'm just going to label all these each time, the difference equation comes with subtracting one number from the other, and the result I get is 6. Now when it comes to setting up equations, this is all that you would look to do. When it comes to solving the equation, you'll learn it in a different video from me down the road. When it comes to what I'm asking, I would also like for these variables to be defined. And I understand that it might be hard for this. You'll see the other equations is going to be a lot easier because there's like context to the problems. This one will be a lot harder to say, what do you want me to say about x and y? They're just numbers. Okay, you could just say x is the first number and y is the second number. That's fine. You can say let x equal first number, y equal second number. But I'm going to get a little bit different with it here. Not weird, but a little bit different because I want to look at this difference equation with you. What happens when you what does it mean when you subtract one number from another and your result is positive? What I mean by that is, how are these 2 numbers comparing? My first number, if I do first number minus second number and the result is positive, what does that mean about first number versus second number? How do they compare? The answer is the first number has to be bigger. It has to be a bigger number. 7 minus 1 is 6, 8 minus 2 is 6, 9 minus 3 is 6, 10 minus 4. You get the gist of it. All of those are 6 in that the first number is bigger because the result is positive. The first number could have been 1, And then the second number is negative 5. 1 is still larger than negative 5. 1 minus negative 5 is still 6. So the point is the first number has to be bigger in order for your result to be positive. So one thing I can say and be very specific with my variables, if I were able to, was say let x equal the larger number. And let y equal the smaller number. There, I defined my variables. We know the numbers do have to be different. If you subtract the same numbers with each other, the difference would be 0. So we know that one's larger and one's smaller. And that's all I'm going to do with that problem. Normally, I'm going to define the variables first. This was an exception because you kind of know what you're supposed to do with the equations here, and there's no real-life context to it. This actually helped us get that. Okay, start to get to some of these other ones where the problems, you're going to see a lot of the problems that we do here, they kind of have the same idea of a setup, but the more that you practice it, I think the better off you'll be. Hear what I say when I set these up. Look at where I point when I create variables and equations and such. Elisa and Brenda are selling fruit for a school fundraiser. Customers can buy small boxes of oranges and large boxes of oranges. Elisa sold 2 small boxes of oranges and 7 large boxes of oranges for a total of $143. All right, that looks like information that's going to be mathy, so I'm just going to go ahead and underline that. I'll use green. Brenda sold 4 small boxes of oranges and 13 large boxes of oranges for a total of $267. Okay, that one's going blue. Now, look, there's no question here because I deleted the questions. I didn't want the focus for my students to be on what's the answer, let's get to that. Now, the question is, what's an approach? What are we searching for? How can we apply this in algebraic form? And, what units are being measured, that kind of stuff. What I don't want them to do is guess and check. It's in essence, it's an algebra class. So, we're looking to say, how can we algebraically come to terms with this? Plus, the answer might not always be an integer. But I hope this one kind of would be, because let's go and take a look at this again. Let's look at the information that we do know and don't know, and how they use these situations here with certain units, like dollars, to state what it is we should be looking for. Elisa sold 2 small boxes of oranges and 7 large boxes of oranges. We know how many boxes she sold. Now, the reason why I'm starting to say all this, by the way, is because you can probably start to say, ooh, I know what variables I'm going to use. I'm going to make a variable for small boxes. And you know what? Let's go and start that. I'm going to make a variable for small boxes. I'm going to call it S. Let S equal small boxes. And there are large boxes. I'm going to use L. Let L equal large boxes. That's kind of fine. But the issue is, what does small boxes mean? If you say let S equal small boxes, what are you saying about those small boxes and large boxes? Let's say I did solve this thing. Let's say that I got answers and I got S equals 10 and L equals 12. What do these numbers represent? Now, I'll tell you what, you might have an answer in mind, but it might be the wrong one. If you say this means there are 10 small boxes, that's not the end goal of this thing. That's not what we're looking for. We know how many small boxes there are. 2 for Elisa, 4 for Brenda. Not that that's supposed to add up to 10. My point is, we know how many there are. That's not an unknown quantity for us. That's not something that we're trying to measure. So it's not about the number of small boxes. Sometimes it is. It depends on the problem. We'd have to look at it. Now, we still might not know what it is, but the point is we can't just say small boxes, large boxes. You got to tell them something about them. It could be number of small boxes, but that's not true for this case. So what is it? So looking back at Elisa, we know how many small boxes she sold. We know how many large boxes she sold. Could this be number of oranges per small box? Well, absolutely it could be. But based on the situation they gave us, when she sold them, she didn't mention how many oranges were in all of the boxes that she sold, like collectively. It doesn't say 143 total oranges. If it did, honestly, that's what I would be defining as my variable. Number of oranges in small boxes and number of oranges in large boxes. But they gave us a dollar amount. She sold 2 small boxes of oranges, 7 large boxes of oranges, and in total she collected $143. Now there are 2 assumptions that we have to make sure that we make here. Number 1, There's no reason to every small box costs the same amount. That's an easy assumption. And every large box costs the same amount. Number two, probably also obvious, small boxes don't necessarily cost the same as large boxes. I assume the large boxes are going to cost more. And not that I'm solving this, but I don't want you to just say like, oh, she sold 9 boxes total, let's divide 143 by 9. No, because you're not averaging how many per box, because there are boxes of different sizes. See, that's why we need two variables, one for the small boxes and one for the large. But how do we define the variables? Well, we know that our total is going to be a dollar amount based on what we sold. So we can make a situation that has to do with her selling boxes. So we have a dollar amount. We know how many boxes she sold. What don't we know? We don't know the price that she sold each box for. So let's define variables as S equaling the price per small box of oranges. Look how specific I'm being here. I probably don't have to put the of oranges part, but I definitely have to include the fact that it's a price. And look at this. I'm going to include that the unit I'm measuring these in are dollars. So if I get S equals 10, what I'm saying in my answer, and I'm not answering them, what I'm saying in my answer is that each small box is $10. It costs 10. She sold them for 10. And L is the price per large box. So now that we know the variables, and this is also important that you say as much as you can, because when it comes to setting up the equations, using this straight terminology helps you understand the variables that you use. And by the way, I promise my other problems will be faster because a lot of the other ones tie in with the same exact kind of thing as this one. So when I go through this one very slowly, you get to register what's happening, see how I'm defining the variables, and see how that continues when I do the other ones and setting up the equations. Okay, there are two equations that we have to do here. Now notice that I made something for green and something for blue. Elisa sold 2 small boxes of orange for $143. It looks like there's a situation that we have that has to do with Elisa's sales. One equation can represent Elisa's sales, that when I combine all the money that I sold, all the money that I made by selling the small boxes with all the money that I'm Elisa, with all the money that Elisa made for selling the large boxes, combined she made $143. It looks like I have an equation I can make given Elisa's information and the variables that I'm using. So I'm going to have an equation that has to do with Elisa's sales. Now, Elisa's sales has everything to do with money, money, money. Everything here is about money. And by the way, everything combines to $143. I already know that this equation is all about when I sell this amount of boxes for this much money, I'm going to make $143. I know this all equals 143 in the end. What I don't know is how to write out terms to represent, and keep in mind what we're trying to represent. The amount of money you made selling small boxes and the amount of money you made selling large boxes. Now I'm going to kind of keep saying that over and over because that is what helps you make your equations. So if you have trouble making an equation with this, and I'm going to get to it, I always suggest to my class use real numbers to try and make an example of it, even if the real numbers are wrong or what have you. Let's put it this way. Let's say, and let's go with what I said before. Let's say she sold 10 small boxes of oranges. If they sell, not 10. Let's say she sold 2 small boxes of oranges for $10 each. How much money did she make selling 2 small boxes for $10 each? Now you say the answer is 20, and you're right. But that's not what we're looking for. What I'm looking for is what did you have to do to calculate that? Most people say 2 times 10. You're not wrong. But what you did was you took the number of small boxes that she sold, 2, with the cost, the price point of each small box of oranges, 10. Now 10 isn't our real number. We don't know what the real number is, so we use the variable s. So one way that I can write this term out is say, if I take 2, the number of small boxes that she sold, and multiply it with the price per small box of oranges, s, what I'm going to get collectively, 2 times s, that's not 25, 2 times S is a term that represents the total amount of money that Elisa made by selling these 2 small boxes. This unit in total is a dollar point. This is all in dollars now. This was number of boxes. This was price per box. Multiplied, it becomes dollars. Cha-ching. The second one's the same way. She sold 7 large boxes. So, when I combine the amount of money made by selling 2 small boxes at this price point, and I sell 7 large boxes at this price point, what is L? The price per large box of oranges. Collectively, you get $143, which is also that unit of measure right there. Dollars plus dollars equals dollars. The units align. Now, if you had trouble with the 7 portion, go back to what I said before about selling them at $12 a box. If you sold 7 large boxes for $12 a box, you do 7 times 12 to make that happen. If you sell 7 at L dollars, and I know that sounds weird, that's why I say use real numbers, you're going to multiply 7 by L. Okay, that's Elisa's sales equation. That's her sales equation right there. Brenda. Is this blue? Yes. Brenda has a different number of sales. Now, they're all selling the same kinds of boxes at the same price points, but they're selling different amounts and they're making different amounts. Brenda's sales is the other equation. Now, if you follow this note, it should be okay. You can say 4 times S, because 4 boxes times S dollars per box. And then 13 times L equals for her $267. You go, Brenda. So there's her equation there. And we're done as far as what I'm asking y'all to do. Well, my class. Now, if I ask you what does 13L represent, you don't want to say, this is really wrong, you don't want to say 13 large boxes. It's not wrong that she sold 13 large boxes. 13 represents the number of boxes sold. 13L is 13 times L. 13 is number of boxes. L is what? Right here, the price per large box of oranges. So what is 13L? The amount of money made by selling all 13 large boxes. It's not 13 large boxes. It's the amount of money made from it. Remember, this is dollars plus dollars equals dollars. And that's what's coming in with all these equations here. And I know I slowed that one down tremendously to make sense of it. But if you have trouble coming up with equations, this is the way to go about it, especially with defining the variables and identifying with what each term means. And these are the harder versions of the problems to do. There are other problems that were like these ones from number 1, which are just, hey, this plus this is that, and that's all good. There could be another thing that said the number of boxes, well, actually, no, I shouldn't say that. But there could be another equation that said the number of small and large boxes combined was 20. So we could do S, well, you have to make different variables. I shouldn't have said what I said. There are other problems that have easier bits. These are ones that have a little bit harder bits because you're converting units into different things. Okay, that problem took a lot out of you. Let's go ahead and do the other ones. Speed up through them, but it's the same talk through them. All right, I just won't use the real numbers anymore. Hopefully you go back to number 2 if you have trouble again. Number 3, Beth and Mofor each improved their yards by planting rose bushes and shrubs. They bought their supplies from the same store. Beth spent $105 on 5 rose bushes and 6 shrubs. Mofor spent $97 on 3 rose bushes and 7 shrubs. Okay, let's get that breakdown. Let's talk about where the information comes from. The first thing, look, the first things, are they important? Sorta. They talk about things, but here's where the information really breaks down. There's information for Beth, there's information for Mofor. All right? Use different colors here to represent them, one in orange, one in kind of a grayish purple. And let's go ahead and define variables for these 2 situations for which we don't know information, for the information that we don't know. And then let's go ahead and write equations based on those. Beth spent $105 on 5 rose bushes and 6 shrubs. We know how many rose bushes and shrubs she has. Same with Mofor. That's not our variable thing. But but they are based on the rose bushes and shrubs. Do we need to know the weight of them? I don't think they have enough information to tell us anything about weight if we wanted to solve, but they have dollars again. Just like number 2, they have dollars. So I'm going to use R and S. They stand for rose bushes and shrubs, but the variables represent something a little more specific. The characteristic that we need, just like number 2, is a dollar point. This time they're purchases though, so I'm going to call it, instead of a price, I'll call it a cost. R is going to represent the cost of each rose bush. And it looks like we're going to use dollars here again. This is in dollars. I'm going to let S equal the cost of each shrub in dollars. There, now that I have the variables defined, this can help me set up equations because I know specifically what the variables represent, and when I say these parts in plain English, I know to tie them in with the variables. Just like the real number scenario from before, that could help you. I'm going to go ahead and try and jump into it without it and see if I can speed things up along the way. I have 2 equations to make. One based on Beth's purchasing situation, one based on Mofor's purchasing situation. So Beth's purchases can be represented in an equation as costing her a total of $105 by combining the amount of money she spent on rose bushes in total, on all 5, and the amount of money she spent on all 6 shrubs. How much money did she spend on 5 rose bushes? You take all 5 rose bushes, each one, and you add up their, you take all 5 rose bushes and you multiply by the cost of each rose bush. There are 5 rose bushes total. You multiply that by the cost of each rose bush. That is R. Multiply 5 with R. 5R equals the amount of money she spent on all 5 rose bushes. Combine that with the amount of money she spent on all 6 shrubs. 6 shrubs times the cost of each shrub gives you the total amount of money she spent on all of those shrubs. That's your equation. You can know, or you can bet how I'm going to do Mofor's equation the same way. So a lot of these equations, again, they're going to sound the same, and that's fine. But it's not just about setting up these equations. It's about knowing what the terms mean and what each item represents. Mofor's purchases, he spent a total of $97 with a different setup, 3 rose bushes. 3R doesn't mean 3 rose bushes. 3 means 3 rose bushes. R means the cost of each rose bush. So that's how much money he spent on all his rose bushes. And then 7 shrubs. 7 shrubs times the cost of each shrub gives you the total amount of money he spent on all 7 shrubs. These are both dollar. This is dollars plus dollars equals dollars, and dollars plus dollars equals dollars. When you get into different word problems, when you get into different word problems, you're going to start seeing a lot of different ways that things are set up. These ones are going to be pretty the same, and these are built for word problems that are meant to solve using what's called elimination. Not that we're doing it, but sorry if these seem a little like the same thing over and over. I do have another video, it's older, I don't know where to have you find it, but I do have another video where I have different sets of comparisons and things, and those might serve to be a little better. This was really meant for how you define the variables and tie in coefficients with problems. So the repeated practice isn't a terrible thing in my view. All right, I'm going to go ahead and jump into numbers 4 and 5, and this should just be going even faster. Number 4, the school that Scott goes to is selling tickets to a fall musical. On the first day of ticket sales, the school sold 6 adult tickets and 5 child tickets for a total of $127. The school took in $190 on the second day by selling 14 adult tickets and 2 child tickets. I sure hope there are a lot more days left and they start marketing this one better, because total, remember, we don't need to know this number, 6 plus 5, 11 is 14. So total they sold 27 tickets in 2 days. Womp womp. I sure hope that this is I sure hope they have a lot more time and they start marketing this one a lot better. Okay, so what are we doing here? We have to define variables. What don't we know? I just mentioned we do know how many tickets are sold per type. Assume adult tickets and child tickets cost different amounts of money. I don't know which one's more. Personally, I don't care. What we're trying to say is, though, we know how many there are. but we don't know their separate costs. Just like the last two problems, they've been dollar amounts. Now, it's interesting that all of these problems are like this because when we did them in class, all of the things were we knew the cost maybe, and we were trying to find out how many there were. But so you can just see that there are different ways that problems are set up, and you have to make sure that you identify which characteristic you're looking for in your variables. So let's go to town with it. I'm going to go ahead and use A and C. Now you don't have to use those letters. You can always use X and Y, but that makes it all the more important that you do define the variables. But we know that A is going to represent the adult tickets. What about them though? The cost. The cost, let's call it price. Price, because I don't know if they're selling or not. Price of each adult ticket, once again in dollars. And then C is going to be the cost of each child ticket. So we've seen a lot of price. So we've seen a lot of these problems now already. Setting up the equations should be a breeze at this point. Oh, not student, child. Setting up equations should be a breeze at this point. But again, I'm going to be using the language so it makes sense with why I'm writing out these variable definitions for a very specific way. I'm going to be pointing to it. And that should help make things hold over a lot more smoothly. Okay, is that my color? No, a little different. All right, so the first one, let's do now. The two equations are represented on first day sales and second day sales. Okay, they're not, here's an adult ticket equation, here's a child ticket equation. This situation is first day sales, and then the next one is second day sales. First day sales rack in a total of $127. That is done by combining the total amount of dollars they made from selling all 6 adult tickets. 6 adult tickets times the price of each adult ticket gives you how much they make there. Combine that with the price of each child ticket times the number of child tickets, 5 times C. Boom, you make $127 by doing that. At least first day sales went that way for Scott. Second day sales is the next one. And once again, different amounts. Looks like, look, they're making more money at this point. Now, it could be a result of, did they sell more tickets? Yeah, 16 tickets versus 11. But looks like the adults are starting to pile in there. So hopefully there is growth. I know this is a made-up scenario, but I like to be optimistic about made-up math problems. 14 adult tickets. 14 adult tickets times the price of each adult ticket, plus 2 child tickets times the price of each child ticket. Money plus money equals money. You've seen 3 equations like this already. I'm done. That's it. Okay, one more problem. Number 5. The senior class at high school A and a high school B planned separate trips to New York City. The senior class at high school A rented and filled 4 vans and 14 buses with 480 students. High school B rented and filled 13 vans and 8 buses with 435 students. Each van and bus carried the same number of students. Now, I like that they gave this last bit of information for this problem here because unlike the previous problems, this one isn't to make that assumption that this would have happened. Whereas if you're selling tickets, that would kind of be unfair that you sold child tickets at one price earlier and then one price the next day. I know they do that in under certain circumstances. But for here, this could always vary, right? Just assume they're just filling up these things and we're only talking about students, not the driver. So in this particular problem, this one's not about money anymore, okay? So don't get caught up in the money aspect. Get caught up in what stuff you do know to make sure those aren't your variables. What stuff the situation gives you as a total when it comes to units to say, what do I need to figure out? And make sure we get our variable for there. Do we know how many vans and buses there are? Yes. 4 vans, 14 buses, 13 vans, 8 buses. The variable is not the number of vans and number of buses. But we do know that when you combine the 4 vans and 14 buses with all those students in, you get a total of 480 students. Assume vans and buses can hold different amounts, buses probably more. We don't know how many students are in each van and in each bus. Those are the variables that we're looking for. Number of students in each van, number of students in each bus. So I'm going to let V equal, this is a number one this time, number of students in each van And I'm going to go ahead and let B equal the number of students in each bus. V doesn't equal vans and B equal buses. And I only say this, look, you might think that, God, why does he keep saying this? Because, God, how many times have I said it to my students only for them to falter? I've seen the mistake over and over. And it's not really, look, it depends on, is the teacher grading that portion or not? Is it so important they define variables? I don't know. But what I do know is people have trouble setting up equations. And they have trouble setting up equations because they don't know what the parts represent. And if they just say V is vans and B is buses, they're kind of makeshifting things along the way. Even if they get a proper solution, they might not be able to articulate what those things mean. If you say V equals vans and you get V equals 20 as an answer, I guess that's a lot of students for a van, but then you might say there are 20 vans. And that kind of, that throws it off. That's not what would have been asked. Not that we see the question here, but that's the point. I want to know that people can define variables despite a question being asked. I mean, and look, the question could ask other things like, what is the product of the number of students? Okay. I only highlighted, or I only underlined one. Oh, I didn't underline my two equations yet. So let's go. High school A, rented and filled 4 vans and 14 buses for 480 students. Let's go and do high school A first. This is high school A's students. High school A's students. It's a lot of vans and buses. All right, here we go. 4 vans, not 4 vans, but 4 vans times the number of students in each van gives you the total number of students in all 4 vans. The total. That's what this represents. If V was 10, it would be 40 total students. All right. Combine that with the 14 buses times the number of students in each bus. Total, that is 480 students. Now, I didn't solve these word problems here, so let's hope that the answers do become integers if you ever did try and solve it and do it right. If you get half a student somewhere, you know something's wrong. You accidentally close the door on them. That's a little morbid, but let's go for it. All right. High school B's students are going to be combined by taking all the students in all of the, where are they? 13 vans and all the students in all the 8 buses. 13 vans times the number of students in each van plus 8 buses times the number of students in each bus equals 435 total. What? Total students. This is students plus students equals students for both sets. Now again, not every problem is set up like these. These are set up to solve using elimination. If you're in my class, who cares what that means at this point? So these were a little bit more the same. So anyway, that's it. I'm done with that. But I'm just saying, sorry if it seemed like they were redundant, that you did them a couple times, but the point is the practice of these particular scenarios. I do have other videos that have other comparisons of other things and items. The problems can get different all depending. Defining the variables is so key to not only setting up your equations right, but also explaining your solution if you have it. And modeling what each equation represents is another way of trying to get the idea of what is it that I'm looking for in the first place? What do these amount to when you add them up? So anyway, so that's what that whole video is about. Looks like I drew over a half hour, but the more you know. So thanks for joining me for this one. I hope you have a good one. Make sure that you ask any questions if you have anything else on there. Take care, guys.